how a harmless compound became a global problem. At first, it was celebrated as a solution so clean, so stable, and so chemically unremarkable that no one imagined it would ever deserve scrutiny. It did not burn, it did not corrode, it did not poison on contact, and it did exactly what it was designed to do: a quiet, dependable consistency. That apparent harmlessness is what allowed it to spread everywhere before anyone realized what chemistry was slowly preparing. To understand why this compound matters today, we need to examine how science defines safety. In chemistry, a substance is often judged by what it does immediately. Does it react violently? Does it degrade quickly? Does it cause obvious harm? If the answer is no, it is labeled stable. That label carries enormous power. It opens doors to mass production, global distribution, and everyday use. Modern society depends on these judgments. Refrigeration, insulation, packaging, agriculture, medicine, and manufacturing all rely on compounds assumed to remain unchanged over time. Harmless means predictable. Predictable means scalable. And scalable means invisible once it becomes routine. This compound followed that exact path. In laboratories, it behaved perfectly. It resisted breakdown. It ignored heat. It passed through systems without reacting. Tests showed no immediate toxicity, no aggressive chemistry, no warning signs. Engineers loved it because it simplified design. Regulators approved it because nothing dramatic happened. The compound earned trust by doing almost nothing at all. This is the first narrative beat. A chemical praised not for its activity, but for its silence. Its refusal to react was interpreted as safety. Its persistence was interpreted as reliability. What no one asked was where that persistence would eventually lead. The second beat followed expansion. Factories scaled production. Applications multiplied. The compound moved into air, water, soil, and products used daily. Because it did not degrade, it accumulated. Because it did not react, it traveled. Because it did not announce itself, it spread unnoticed. At this stage, nothing felt wrong. The compound remained chemically polite. Systems worked. Costs dropped. Efficiency increased. Success reinforced belief. The more it was used, the safer it seemed. After all, years passed without obvious consequence. The third beat began subtly. Measurements improved. Detection limits dropped. Scientists started finding the compound far from its intended use. In places it was never meant to be. In concentrations no one had predicted. Still, it appeared inactive. Still, it seemed harmless. But chemistry does not require aggression to cause damage. It only requires persistence. And this is where the story begins to darken. Because once a compound enters every system, without breaking down, it stops being a tool. It becomes an environmental participant. And chemistry never allows participation without consequence. As the compound continued circulating, chemistry began revealing a quieter truth. Inactivity did not mean irrelevance. Stability did not mean isolation. The compound was not reacting, but it was interacting in ways no early test was designed to observe. At first, these interactions were dismissed as background noise. Trace detections in water samples, minute concentrations in soil, microscopic presence in living tissue. The levels were low, the effects unclear, and because the compound did not degrade, measurements kept rising slowly year after year without triggering urgency. Chemistry was not misbehaving. It was doing exactly what persistence demands. This is where the reveal deepens. A compound that does not break down does not disappear. It accumulates across systems that were never meant to store it. Air carries it, water dissolves it, soil traps it, living organisms absorb it without mechanisms to remove it. What began as a localized solution became a global distribution network powered by nature itself. Inside biological systems, the compound behaved strangely. It did not kill cells. It did not disrupt immediately. Instead, it occupied space. It bound weakly to proteins. It lingered in tissues. It altered chemical balance by presence alone. Subtle shifts appeared in hormone signaling, enzyme efficiency, and cellular communication. Nothing dramatic, nothing obvious, just persistent interference. The early conflict forms here. because toxicity testing was designed for short-term reactions, acute exposure, clear symptoms, fast outcomes. This compound did none of that. Its danger was cumulative. It required time, repetition, generations. Chemistry was operating on a scale regulation was never built to monitor. As concentrations rose globally, patterns began emerging. Wildlife showed unexplained changes. Reproductive rates shifted. Developmental anomalies appeared. Still, causation was hard to prove. The compound was everywhere. So was uncertainty. Chemistry hid behind complexity. What nobody expected was how difficult reversal would be. Removing a persistent compound from a global system is not like fixing a machine. There's no off switch, no recall, no containment once distribution reaches air and water. The very stability that made the compound useful now made it permanent. Industries face a reckoning. The compound still performed perfectly in products, but outside controlled environments, it had become something else entirely. Not a reactant, not a poison, but a background chemical reshaping systems simply by refusing to leave. This is where tension tightens. Because the compound did not fail, it succeeded too well. And chemistry began exposing the cost of a substance that never stops existing once it is released. As evidence accumulated, the true scale of the problem became impossible to ignore. The compound was not isolated to one industry, one region, or one use case. It was embedded everywhere, threaded through ecosystems with a reach that mirrored globalization itself. What once felt contained had become systemic. This is where the conflict fully reveals itself. Because chemistry had done nothing extraordinary. The compound behaved exactly as designed. Stable, persistent, non-reactive. The mistake was assuming those traits were universally safe. In reality, permanence is one of the most disruptive properties a molecule can have. Inside living systems, the compound began acting like chemical static. It did not trigger alarms. It did not destroy structures outright. Instead, it interfered subtly with signaling pathways. Hormones misfired. Enzymes slowed. Developmental timing shifted. Effects varied between species, ages, and environments. That variability made denial easy and action slow. The buildup intensified as generations passed. Because persistence compounds across time. Each year of release added to the previous one. No degradation meant no reset. Baseline levels rose quietly until exposure was no longer exceptional. It was normal, and normal made it dangerous. Industries responded cautiously. They questioned data, demanded proof of direct causation, argued benefits outweighed risks. And in narrow contexts, they were right. The compound still worked. Products still performed. Alternatives were costly, less efficient, or untested. Chemistry had created a stalemate. Meanwhile, remediation proved nearly impossible. The compound resisted breakdown by heat, light, and microbes. It moved freely through water systems. Filtering it required enormous energy and infrastructure. Cleanup was not just expensive. It was incomplete by design. Once released, the compound could not be fully retrieved. This is where tension peaks. Because the world was now living inside a chemical decision made decades earlier. No single actor could undo it. No single policy could reverse it. Chemistry had already integrated the compound into planetary systems. The problem was no longer usage. It was inheritance. At this stage, the question was no longer whether the compound caused harm. It was how much harm was acceptable and who would bear it. Chemistry does not answer those questions. It only ensures that consequences persist as long as a molecule does. The climax is not discovery. It is permanence. The world finally understood that the compound was never dangerous because it reacted. It was dangerous because it refused to stop existing. Chemistry had created a substance that outlived intention, regulation, and responsibility. Once released, it became part of the planet's background chemistry, influencing systems simply by being present everywhere at once. This is the central realization. Stability is not safety. Inert does not mean harmless. A molecule that resists breakdown also resists correction. When chemistry creates permanence, it transfers responsibility from design to eternity. And eternity is not something systems are prepared to manage. The resolution is not reversal, because reversal is no longer possible. The compound cannot be recalled from oceans. It cannot be filtered from rain. It cannot be removed from soil at planetary scale. Chemistry has already accepted it into circulation. The only remaining control lies in limitation. Modern relevance makes this lesson unavoidable. New compounds are being designed every year, more stable, more durable, more resistant, and each one carries the same question forward, not just how it performs, but how long it will remain once it escapes containment. Because escape is not hypothetical, it is inevitable. This reframes responsibility at the molecular level. Design is no longer just about usefulness, it is about exit. How does a compound end? How does it degrade? What happens when it spreads beyond intention? If those answers do not exist, chemistry will provide them later, without consent. Once you see this, harmlessness feels different. Silence feels suspicious. Stability feels conditional. Every molecule becomes a long-term participant, not a temporary tool. And participation always reshapes the system. How a harmless compound became a global problem is not a story about mistakes. It is a story about forgetting that chemistry never forgets. Every molecule released becomes part of history, and history, unlike products, cannot be discontinued. How a